All right. Welcome back. There's just one more thing I wanted to point out in terms of the Wittig reaction and synthesis. When you're doing retrosynthesis for the Wittig reaction, sometimes you're going to have a choice as to, because as we pointed out with the color, when you look at an alkene and think, how could I have made that via a Wittig reaction? One of the carbons of the alkene comes from the aldehyde or ketone. The other comes from the phosphonium ylide reagent. And your question is, which should be which? Notice that the preparation of the phosphonium ylide reagent required an SN2 reaction. And remember that SN2 reactions are faster for primary alkyl halides than for other types of alkyl halides. So if you have a choice in a Wittig reaction, you should choose the phosphonium ylide to be on the side that could go through the less substituted alkyl halide, because that SN2 reaction is going to be faster and more efficient. For example, in this case, I would choose the aldehyde side or ketone side to be that one, and this side to be the phosphonium ylide side. I'm going to use the red squiggle mark in my retrosynthetic analysis to indicate which set of bonds I made in this Wittig reaction. Again, I'm going to choose to use this side as the ketone, and then the other side as the phosphonium ylide reagent. That distinction may not make sense at this stage until I remember that I could have made that phosphonium ylide reagent from, whoa, that's me, isn't it? How bizarre. Do I really sound like that? How can you guys stand that? Oh, brother. People sometimes talk about dying and watching the movie of their life. I really hope that's not a thing. I don't think there's a whole lot I want to see again. Okay. So do you see how this is a better pathway than the alternative? We could have chosen to make this side the phosphonium ylide and this side be the ketone or the aldehyde, but that would have required an SN2 reaction on a secondary alkyl halide, which might have been okay, but if you have a choice, you should go with the one that you definitely know is going to be easier. Okay. Less, better, no. This is way before any of your time, but prior to Preach My Gospel, we had something called the Missionary Guide. It was this purple manual, and there were a lot of helpful things in the Missionary Guide, lots of helpful role-playing, including more effective and less effective examples. In Spanish, that was menos eficaz, and you didn't ever want to be menos eficaz. So anytime I write less effective, that's now got a whole bunch of emotional baggage attached to it. Okay, so chapter 15 is carboxylic acids. A lot of this is a review. Your study guide takes you through a lot of it. We won't spend a lot of time on stuff that's review. For example, it should be obvious to you which of these two is more acidic and why. Go. Well, on the right's more acidic. Why? Inductive effect. That's chloro is more electronegative than carbon. The carbon-chlorine bond is polarized. That makes the carbon somewhat electron poor, which allows the carbon, I'll call that the alpha carbon, to pull electron density away from the carbonyl carbon. All of this is about stabilizing the negative charge in the conjugate base. Acids are acids because they can tolerate the electron density in the conjugate base. And you're being better able to spread out the negative charge via an inductive effect is what stabilizes the conjugate base. That makes the corresponding acid much stronger. You can look at pKa's. I happen to have some numbers written down. That inductive effect is worth about a factor of 10 or more in equilibrium constant. The pKa of alpha chloroacetic acid is 3, which is 1 log unit lower than for a typical acetic acid. I don't actually have the number written down for trichloroacetic acid, but it's even more acidic, right? So you've thought about the inductive effect that way. Another place that this shows up in your text is when thinking about benzoic acids. So this carboxylic acid is called benzoic acid. That's where the benzene ring is directly attached to the carbonyl carbon. Functional groups on the benzene ring strongly influence acidity. So for example, putting a nitro group on the benzene ring makes it more acidic. In contrast, putting, well, maybe we'll just leave it there at that point. The nitro group makes the benzoic acid more acidic than just regular benzoic acid for reasons that we can talk about. It's actually easiest if we draw the conjugate base of nitrobenzoic acid. You might be inclined to think that all of this has to do with the inductive effect because nitrogen is more electronegative than carbon. And that's a reasonable starting place, but it's wrong. And the reason for that is the inductive effect drops off the farther the electronegative atom is from the place where the negative charge is in the conjugate base. By the time you're, 1, 2, 3, 4 atoms, 4 or 5 atoms away, the inductive effect really doesn't matter anymore. So what's actually going on here has to do a little bit with resonance. And to show you this, I'm going to draw for you the actual Lewis structure of the nitro group. What I'm going to tell you now is something that will become important to you in a subsequent chapter. But notice that in the nitro group, I have adjacent to the benzene ring, I have an atom that's doubly bonded to an oxygen. When that's true, I can draw a resonance structure where I break the bond between the nitrogen and the oxygen, move the pi bond out onto the oxygen as a lone pair, and then move this pi bond from the benzene ring out to form a new carbon-nitrogen pi bond. So let's just draw that resonance structure. And a positive formal charge on this oxygen in the ring. Now, those of you that took my 351 should be having a little bit of PTSD because you're sensing a question, which is which carbons in the ring share that positive charge? Do you know? Better know. I'm perfectly capable of resurrecting that kind of question for an exam. You can draw resonance structures in which the positive charge in the benzene ring is on either of the pink carbons. I'll show you this resonance structure and then ask you a question. How does this resonance structure explain the increased acidity of para-nitrobenzoic acid over just benzoic acid? What do you suppose is going on here that stabilizes the conjugate base?
Yeah, go ahead.
I mean, it kind
kind of gives a spot for the electrons to go. They can go into that ring there.
Okay, kind of gives a spot for the electrons to go. Is there any way for me to push arrows to move the electrons on the conjugate base into the benzene ring? There's not really. I can delocalize the lone pair electrons on the carboxylic acid oxygen out onto either oxygen. I can't get them to the benzene ring, but you are right that having the positive charge adjacent to the benzene ring does have an effect. That's sort of, it's sort of an inductive effect, right? You have an electron poor carbon adjacent to the carboxylic acid. That's pretty similar to what we had up here with the chloro on the alpha carbon. So people look at this example and they want a simple answer. They want to say it's resonance or it's the inductive effect. It's actually both. It's resonance electron, it's withdrawal of electron density by resonance. Nitro group is an electron withdrawing group because of resonance. The nitro group makes the benzene ring electron poor. The nitro group puts a positive charge in the benzene ring, including on the carbon that's adjacent to the carboxylic acid. And then the electron poor benzene ring pulls electron density away from the carboxylic acid via an inductive effect. So this is a combination of two things. You need resonance to make the benzene ring electron poor, and then you need the inductive effect to suck electron density away from the carboxylic acid. All right. Questions about that? Yeah.
So there's two other resonance structures that don't have that positive charge on that carbon. Does it mean that it has more of an electron donating effect over the electron withdrawing effect?
There are two other carbons that don't have positive charge there.
In reference to the other two resonance structures,
Oh.
you put the positive charge on carbon 3 and carbon 5.
Okay. I'm not sure which one is 1, 3, or 5, but there we go. I guess you're noting that only in the resonance structure when the positive charge is on carbon 1 do we have the positive charge adjacent here, and you're asking does that have an effect? Maybe, though with resonance you need to think of that positive charge as just being delocalized across all three carbons, not switching back and forth. Yeah. Okay. All right. There's more we could say there. I think that's probably good enough. All right. We want to talk. What I'm going to show you now is a review from. Also from 351, and again, maybe you're going to experience a little bit of PTSD. This is how to use pKa's of acids to determine whether they're in their acidic or conjugate base forms as a function of pH. This is the Henderson-Hasselbalch equation. There's a section in the chapter about that you can review. I'm not going to derive that equation for you, but I will show you what it looks like and how you can use it. Sure, this will work. Comparing pKa of a particular acidic group with the pH of the buffer that it's in can tell you how much of the acid that we're talking about is in its acidic form versus its conjugate base form. This is the so-called Henderson-Hasselbalch equation. Note, we are not using it in the way that you used it in general chemistry. In general chemistry, you probably were taught to use it like this. If I've done the math right, I think both of those are true. in general chemistry, you use this equation in this form to answer the question, if I want to make a buffer and I know what the pKa of the acid form of my buffer is, and if I add the buffer in a ratio of acid form to base form that is known, I can get buffer with a particular known pH. You've done that before. Multiple PTSD experiences today. All of a sudden you're back in the testing center and it's Chem 106 and you're angry. My son just finished taking Chem 106 and there was a lot of angst, so I get this. That form is useful if you're a lab tech making buffers for a biochemistry lab, but that's not how we're going to use it in this class. In fact, in the setting of organic chemistry in biochemistry, pH is going to be constant. You better hope pH is constant biochemically. This is why we're all alive and breathing now, is because the pH of our blood is held constant. The thing that we're going to be doing is looking at, as a function of pH and the pKa of a particular acid group, which form dominates, the acid form or the conjugate base form. Let me give you an example. In my lab, we do a lot with peptides and proteins. And so I'm going to use, because peptides and proteins are so large that it's difficult to draw them, I'm going to abbreviate and just use this lovely squiggly line to represent a protein that forms what's called an alpha helix. You may have heard that term before. We'll talk about that in detail in a subsequent chapter in 351. In a particular experiment that we have, I have two different proteins that each are able to form alpha helices. One of them has a lot of side chains on it that look like this. I'm really, really abbreviating. And the other has a lot of side chains on it that, don't like that look like this. There's a lot of other kinds of amino acid side chains that we could be thinking about. Now, I will tell you that in our experiments, pH is 7. And then we need to identify what the pKa's of the various side chains are on this peptide or protein. If we look it up in a pKa table, you would find that a carboxylic acid like this usually has, and we can highlight the acidic protons with purple, carboxylic acids usually have pKa's around 3 or 4. For this particular amino acid side chain, we'll just say 4 is the pKa. So, compare pKa 4 to pH 7. 4 minus 7 is negative, right? So what does that tell me about this ratio? Greater than 1 or less than 1? Less than 1, right? If this number is negative, for logarithms to be negative, the thing inside the logarithm has to be less than 1. That tells you which form dominates. The base form, the negatively charged form. So at pH 7, this should really be negatively charged. This one should also be negatively charged. And this one should also be negatively charged. Okay? Expect a net charge of -3 on this particular molecule. Amino groups, the bane of many of 351 students' experience. We'll go through this. I don't know how to say it any clearer. The only way you're going to get this is to make mistakes multiple times. Some of you, perhaps in your past, have lost somewhere between 8 and 10 points a couple of times over this mistake. So please do not do it again. When you look at a neutral amine, your first natural inclination is to focus on the neutral amine going to its negatively charged conjugate base. And if you look that pKa up in a table, it's 38. There is a reason why that never, ever, ever, ever in a gazillion years ever matters in aqueous solution. Why? In all of your experience in Chem 106, did you ever hear someone tell you the pH is 39? No, can't happen, right? In part because you can't get hydroxide that concentrated in water. All right? So if pH is 7, what's the deal with the purple proton? Is it on or off? On, always, never comes off. You never make this conjugate base ever, 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 ever in water by a factor of 10 to the 31, which means never in the history of the universe in water. Okay? All right. So then, and I think actually most people that get my questions wrong on 351 exams realize that. What they forget is that there's another acid-base equilibrium, just like there was another Skywalker. Ooh, that was not a good segue. Just as there was another Skywalker, there is another acid-base equilibrium for amines. That is, neutral amines have positively charged ammonium conjugate acids, and their pKa's are 11. So it's not just the purple proton you have to worry about, you also have to worry about the orange proton, the extra one. Okay? All of these have positively charged conjugate acids whose pKa's are around 11 ammonium ions. And compare 11 to 7, tell me at pH 7, what's the deal with the orange proton? Is it still there or is it gone? Still there, right? The pKa of the ammonium is high enough that the neutral amine doesn't exist in aqueous solution at pH 7. It's just majority ammonium ion. So that tells you that at pH 7, the positively charged conjugate acid dominates. Why is this important? Well, for us, we use this in our lab to make sure that that we can put these two, the black and the red peptides, in solution, and they will preferentially associate with each other because they have opposite charge. And that kind of thing ends up being important a lot in biology. So when you learn later on about amino acid side chains, you're going to need to be able to do what we've just talked about here, where you use the pH and then the pKa of a side chain to determine whether the side chain should be protonated or not. One more example. Here is a large protein, and we'll simply draw some other functional groups on it. We'll put the neutral amine. Actually, well, whatever. We've already done both of these two. We'll do a couple of other ones. Some of what I'm drawing, or most of what I'm drawing, are amino acid side chains that you're going to encounter later on in the class. I think that's probably enough. Maybe one more. You would have, though you don't have in front of you right now, but you would have a pKa table which would contain pKa's for all of the relevant pKa's for these side chains. The trick is I'm always going to draw them for you in neutral form. If I don't, then it's not a hard problem. So you got to be good at recognizing among the neutral forms of these amino acids, recognizing side chains which have negatively charged conjugate bases and side chains that have positively charged conjugate acids. So as an example, of course, you know, there's an amino acid that has a pKa of around 4 and the conjugate base is negatively charged. Here's another negatively charged conjugate base, the phenolate ion. Here's another negatively charged conjugate base, the so-called thiolate anion. The others do have negatively charged conjugate bases, but their pKa's are so high as to not be important in aqueous solution. So what I'm going to do instead is just draw the positively charged conjugate acid. Oops, I wanted an orange highlighter there. Here we go. And these positively charged acids would be present on the pKa table, but you'd need to go look for them. For this particular side chain, for example, I wouldn't even show you the pKa of this neutral amino acid because it's high enough that it doesn't matter in aqueous solution. Instead, I would just have shown you this positively charged conjugate acid. Same thing for this functional group. You would not find that neutral amino acid on the pKa table. Instead, you would just find the positively charged conjugate acid. Okay? And you could look those up. If we look them up, you would find pKa's of, 10 here, 4 here. This pKa is 11, this one is 6, and this one is 12. So let's just highlight the forms that should dominate at, let's pretend we're in the lysosome. The lysosome is a subcellular compartment that has acidic pH. I'm not exactly sure what the pH is. Let's just call it 2. Probably isn't that low. Somebody can look it up. But in any case, let's just pretend pH is 2. Let's highlight in gray the form of each amino acid side chain that should dominate at pH 2. All right, what do you got for this one? Neutral or negative? Neutral. Why? Lower than the pH is lower than the pKa. Good. Okay. How about the phenol side chain? Neutral or negative? Neutral. Again, 2 is less than 10. All right. How about the amine side chain? Neutral or positive? Positive. Absolutely positive. Good. The thiol side chain. Ooh, I forgot to tell you that pKa. That's around 8. Neutral or negative? Neutral. How about the, you don't want to know the name of that functional group, imidazole side chain. This is imidazolium. Neutral or positive? Positive. 2 is less than 6. How about, you don't want to know this one either. This is guanidinium. Neutral or positive? Positive. Okay. So this question might ask, what's the net formal charge on this peptide? Just count up the charges. Looks like we've got 3 neutral side chains, 3 positive, so 3 plus. Okay? Yeah?
Would you ever have, so like on like an exam, for example, would you give us a similar question like this? Or would you ask us more about like calculating an isoelectric point for like a amino acid or
Okay.
a mixture?
Yeah, so there is a, if you know all the pKa's, you can do some math to calculate a pH at which the molecule would be neutral. That's called an isoelectric point. You may learn about that in biochemistry. I won't have you do that. Yep. Okay, good. All right, So be able to do that. One thing that we want to do in this chapter is just talk briefly about phosphoric acids, because when we get to the chapters on metabolism and in biochemistry, you're going to be seeing lots of phosphate groups. We're going to be thinking of them as leaving groups as well, and we've framed the concept of a good leaving group in the past by saying that good leaving groups are conjugate bases of strong acids. So it's good to learn a little bit about phosphorus kinds of acids so that you can apply your pKa-based intuition to biochemical groups that have phosphates on them. So, back to Gen Chem, you certainly encountered phosphoric acid before. This was an example of something out of your nightmares, a polyprotic acid. Remember those words? The first proton on phosphoric acid has a pKa of around 2. It's in equilibrium with the monoanion, or sometimes called dihydrogen phosphate, or H2PO4 minus. Somewhere in your mind, Celine Dion is singing "It's All Coming Back to Me Now." This pKa is around 7.2. That's close to physiological pH. So actually phosphate buffer is a really good buffer for biochemical experiments because you can keep the pH pretty close to physiological pH. So that's dihydrogen phosphate. It's in equilibrium with monohydrogen phosphate, HPO4 2 minus. That last pKa, should have brought my reading glasses today, for the final proton is actually pretty high. It's around 12. I need to slide some things over. And so the final just phosphate anion, PO4 3 minus, is that structure. So based on these pKa's, you can see that at physiological pH, if pH is 7, there should be basically a 1-to-1 mixture of H2PO4 minus and HPO4 2 minus, right? Should be about 50-50. And that's generally true. Okay? So why do we care about this? For a couple of reasons. It can tell us sort of what to expect when we're looking at biological molecules. So for example, what I'm going to draw for you here is glucose 6-phosphate, which is an intermediate in the metabolism of glucose through the process called glycolysis. Glucose 6-phosphate has carbon 6 is oxygen instead of being an alcohol. It's involved in a functional group called a phosphoester. Phosphoric acid, carboxylic acid. Phosphoester, regular carbon-based ester. Notice that in an ester versus a carboxylic acid, one of the OH group is actually an OR group. Here's phosphoric acid, here's a phosphoester, that's the OR group. So we'll talk about phosphoesters as functional groups. Nevertheless, you can look at the pKa's of the protons on phosphoesters, and they track pretty much like you would expect for protons from phosphoric acid. So we can use that information to predict what that functional group is actually going to look like at pH 7. So tell me, at pH 7, is the pink proton still on? No, it's going to be gone. At pH 7, what about the orange proton? Half and half. How do you draw that? You don't, you just pick one. So it would be totally reasonable at pH 7 for me to draw glucose 6-phosphate as follows. Oops, gotta have the oxygen. It would be totally okay for me to draw it like this. It would also be totally okay for me to draw it like this because both forms are probably present at physiological pH in about a 1-to-1 ratio. Okay? And in fact, some biochemists will actually hedge, and instead of drawing out the Lewis structure of the phosphate, oh, I really don't like that chair, they will just abbreviate PI there, which stands for a phosphate group, and you just have to know what they're talking about. Okay, the I actually stands for inorganic phosphate. That's an old-timey choice of a way to talk about phosphate, but this way you'll sort of understand what people are talking about when you're in biochemistry. Sometimes, most of the time, I'm going to choose this structure of the phosphate ion just out of habit. You're free to draw it this way or this way in the phosphoester. The other time this will show up is in DNA, nucleic acids. You've heard about phosphodiesters. So notice that in the phosphoester, one of my oxygens, one of my 3 OH groups from phosphoric acid is an OR group. In DNA, oops. So I'm going to have mercy on you, and we're just going to use A for adenine for DNA. What should we do here? Here is the phosphorus. In DNA, 2 of the 3 OH groups from phosphoric acid are replaced with OR groups. Squiggly line there means there's other stuff down here that we're not talking about. And then let's do, I don't know, C. Squiggly line there means there's other stuff there that we're not talking about. This functional group here is called a phosphodiester. Unlike carboxylic acids, phosphoric acids can be attached to more than one OR group. Okay, so that's the phosphodiester. We've still got one OH group there, but based on what we looked up above for carboxylic acids, that pKa should be around 2. So at physiological pH, is that proton on or off? Off. That's really important because that tells you that this part of the DNA molecule at physiological pH should be negatively charged. People will talk about this as the sugar phosphate backbone of DNA, and these are the nucleobases. The sugar phosphate backbone of DNA is negatively charged. Yeah?
Let's say that you give us like an antiviral drug with like positively tipped end or like potentially like a negatively tipped end that could interfere with that phosphodiester in the 3 to 5
Okay.
connection right there. Would you give us like that's just one example of an interaction with like an antiviral drug?
Okay.
Would you expect us on an exam maybe later on to give us like an antiviral drug and predict where in the DNA chain it would interfere?
No, so what you're describing is something that's probably beyond the scope of the class. However, you will discover in biochemistry, and if you take a biochemistry lab, there are fluorescent dyes that you use to visualize DNA when you're running a gel, an agarose gel. And one of these is called ethidium bromide. It's got a positive charge on it, and so that helps it selectively associate with the DNA backbone. No, we probably, I mean, there's not a great way to write an exam question about that, but you're seeing that there, just by noticing that the backbone is negatively charged, you're thinking of some intermolecular forces that you could use to bind to and recognize DNA. And there are transcription factors and other molecules that bind DNA that do take advantage of these negative charges. Yeah. Okay. So we could move into chapter 16, but actually I think I want to stick with biology for just a minute. Your text always has these sections: interesting aldehydes, interesting carboxylic acids. I'm never sure what to do with those sections, because interesting, if you have to tell somebody that it's interesting, it might not be. At the same time, and I'm always worried about what to do here, because I know that when I bring in stuff that is just interesting, automatically you want to know, is it interesting enough that it's on the exam? And if so, what is the question? And in particular, what is the right answer for that exact question? That's all I want to know. I'm not really into you memorizing the structures of large molecules. Recognizing them could be one thing. Again, the standard is you want it to appear after you've taken the test, like you were here today and listening. I'm infamous, actually, in 351. I did this for the first time last semester. Some of you were there. We talked about non-covalent interactions. We talked about functional groups. We talked about how some esters have fruity smells. Question on my 351 exam, I kid you not, which of these smells like banana? And, you know, some people were like, I didn't know I needed to study that. And I'm like, were you in class that day? Were you listening? I didn't actually say that. But anyway, so just know enough so that it appears that you were here and listening. There's an interesting story with carboxylic acids and pain relief that we could talk about. The first is this carboxylic acid, which is called salicylic acid. It's a benzene ring with an OH group and a carboxylic acid on adjacent carbons. Please don't memorize that that's the structure of salicylic acid. This can be isolated from a plant called meadowsweet. And this was originally discovered a long time ago for its sort of anti-pain properties. Salicylic acid also has some topical uses, like if you for treatment of acne and stuff like that. But it also has some pain relief characteristics. And for a while, its conjugate base, sodium salicylate, was sort of the only thing you could use to treat pain. Salicylic acid ended up being irritating to mucous membranes in the mouth and in the stomach, so you couldn't actually give people salicylic acid. You could give them the conjugate base, sodium salicylate, but for some people it was just cloyingly sweet. They couldn't tolerate it. So a German chemist in the late 1800s, just towards the turn of the century, named Felix Hoffmann developed the synthesis of a related molecule, a derivative of salicylic acid that would do basically the same thing, but could be formulated as a pill, as a solid that could be swallowed without you having to taste it. And his work, his name was Felix Hoffmann, and his work was motivated by his father suffering from rheumatoid arthritis, being in terrible pain, and yet not being able to tolerate the sweetness of sodium salicylate. I've never tried it, and I'm with some of you who may be thinking, is there such a thing as too sweet? Like, could it be that bad? I think it actually is that bad. And so the solution actually is a very, very sensible chemical solution. I'm not talking about a solution like an aqueous solution, this solving the problem. It was to make an ester out of the OH group. This is now acetyl salicylic acid, and that's aspirin. First synthesized and sold in 1899 by the Bayer company in Germany. Made them $1 gazillion, tons of money. Company still exists. You can still buy Bayer aspirin if you want, though you probably shouldn't because it's available much cheaper from generic sources. And for a long time, actually, it was not known what the mechanism was for why this works as a pain reliever. Anyway, it was in a form that could be, you didn't have to taste, and so it was a much, much better drug. That's aspirin, acetyl salicylic acid. It's an example of what are called non-steroidal anti-inflammatory drugs, or NSAIDs. That tells you what it does. We didn't used to know that. The Nobel Prize for discovering aspirin's mechanism of action as an anti-inflammatory agent was awarded in the 1970s. It was awarded in 1982, discovered in the 70s. And the story with carboxylic acid sort of continues. Aspirin inhibits the synthesis of a class of molecules that are called prostaglandins. So this is going to be dumb because these are large molecules. Please don't draw them. They're in your text. I'm going to draw the precursor of prostaglandins. This is a long-chain carboxylic acid, one of the fatty acids that we have talked about previously. This is called arachidonic acid. It's a 20-carbon polyunsaturated carboxylic acid. And a class of enzymes called cyclooxygenases. You'll know why they're called cyclooxygenases in a minute. Takes this simple arachidonic acid and converts it into a precursor of prostaglandins. Here's the cyclo part. You cyclize some of the atoms to form 5-membered rings. Here's the oxygenase part. You put oxygens in on the carbons where they weren't there previously. Those of you that took my 351 final have seen molecules like this before. There was a big, nasty stereochemistry question involving prostaglandins. Look at all those stereocenters and all the chances to assign E versus Z. It was fantastic. This is called prostaglandin PGF2 alpha. And prostaglandins have a lot of interesting biological functions, but they are associated with pain and inflammation. They're not hormones. They don't get synthesized and then released into your blood. They're actually synthesized on site where the inflammation needs to occur. And so if you can inhibit their synthesis on site, you can decrease the effects of inflammation. And aspirin and other NSAID drugs interfere with the cyclooxygenase enzyme that creates the prostaglandins. There's another story that you'll have to get from one of your biochemistry professors later on Professor Dan Simmons, who's an emeritus professor here at BYU, discovered a second cyclooxygenase enzyme called COX-2, and that led to discovery of COX-2 inhibitors that were developed by Pfizer and others for treating pain, and that the patent that Professor Simmons generated because of his discovery of the COX-2 enzyme actually led to a significant amount of licensing money being paid by Pfizer to BYU, which funds the Simmons Cancer Research Center and a lot of the undergraduate research assistantships that are in the chemistry department for research students. So anyway, that's the story with carboxylic acids. We will continue next time with chapter 16.